Welcome to another video for Stat 420. In this video, we're going to be introducing kind of the one-way ANOVA method for analyzing data that's split across groups. And we kind of start off with this idea that we're really building a model with one categorical predictor when we're doing one-way ANOVA. And honestly, this model kind of works for a two-sample t-test as well, if you want to think about a two-sample t-test as a comparison of a response variable against a factor with only two levels. So I could actually use this model in a two-sample comparison as well, but in general, we can use it for as many factor levels as we want, for as many countable factor levels as we're looking at. So this model might have some familiarity to the simple linear regression model that we've seen before, which is going to look like y sub I equals beta naught plus beta 1 times x sub I plus some random noise for that ith observation. So the first thing that I'll kind of point out here is that beta naught and mu serve very similar purposes in these models. Beta naught is an anchor for that model to where it crosses the y-axis. So it just tells us we might have a particular slope, but beta naught tells us where that slope is going to be located and where it crosses the y-axis. So mu over here does a similar thing where it tells us where kind of this overall, this global mean, as we'll call it, is going to be positioned. And alpha is going to represent the particular effect, the particular average difference that we observe from mu to that particular group's, that particular level's actual mean. So mu represents kind of the global mean for this response across all groups, whereas alpha sub I represents the mean of a particular factor level. So maybe for like this level, alpha sub I is negative, meaning that the true group mean is actually over here. For this group, maybe alpha sub I is positive, signaling that the true average for this group is actually a little bit up here. So that's what alpha sub I kind of represents there. So in a sense, alpha sub I replaces beta 1 times x, because in simple linear regression, we are modeling based on the actual value of our predictor variable, which is going to be a numeric variable. When we're doing something like ANOVA, we aren't modeling based on the numeric value of our predictor, because we don't necessarily have that. Instead, we just have these separate individual groups which don't have numeric inputs. I just have groups like red light, green light, natural sunlight. And I'm just kind of labeling them group 1, group 2, group 3. They're not in a particular order. They just represent the groups that I'm comparing, and they each have kind of a group effect that's possibly at play that I want to model. And then again, there's a random error term just to represent the fact that when I'm modeling an individual observation, my model is not going to reflect the random noise that is going to exist in my data. It's going to be the other things that affect the response variable measure besides the grouping factor that I'm looking at. So every individual observation is going to have a random noise component to represent how much kind of unexplained variability is still left in the response, even after accounting for which group it comes from. In terms of notation, the I is now going to represent the number of groups I have. So I equals 1 means group 1, I equals 2 means group 2. J is going to represent the number of observations in a particular group. So I'm going to have, n observations in group I, and I'm going to have, some other number of observations in group 2. Sorry, that's really confusing. So I may or may not have the same number of observations per group is what I'm trying to say. Maybe I do, maybe I don't. But J is going to represent which number observation a particular observation is within a particular group. So, for example, I might have y sub 2, 7 would be the 7th observation in group 2. All right, so here's kind of a visual aid to think about what we're doing. Let's just kind of think about this as like plant growth, since we've talked about that before. It's not super consistent with the y-axis I have over here, since apparently these values can be negative, but let's pretend that's not the case. So if I'm looking at, say, plant growth, what I might do first is recognize how much variation I have in plant growth across all the plants in my study. This represents kind of that full amount of variation that I see, that there's a lot of different outcomes going on over here. But if I haven't split it up by factor level, I might be missing some way to kind of explain these differences. So if I go over here and split it up by which group they came from, which experimental treatment it received, I might notice some systematic differences between each of my groups related to plant growth. So even though I kind of have this estimate for the global mean, so this is kind of my estimate for mu, my estimate for the true average plant growth across all groups is represented by this horizontal line. It's still represented over here. So this is my, here, I'll do this as a double arrow. So I'll call it a sample estimate for mu. I could also call it x bar, right? So like x bar is my estimate for the global mean mu. That's totally fine. And you'll notice on the left, it's just the mean of the combined group. On the right, though, it's a line that gives me kind of a reference point for how far or how much the particular factor levels seem to be kind of affecting the plant growth possibly here. Because I have some individual group means as well, right? So for group A, it looks like the sample mean is somewhere around here, maybe. For group B, it seems like the sample mean is much higher, like maybe up around here. And for group C, it's going to be somewhere maybe in here. It's kind of hard to tell. So what's going on here is I want to kind of account for these group-specific differences in the response. So in other words, knowing which factor level it came from tells me something about where I expect to see this plant growth, or at least it gives me kind of a better starting point, right? So instead of starting from the global mean or my estimate for it, I'm going to start from the group mean as kind of my best estimate for growth in that particular group. So this right here is like alpha sub 1. This right here is like alpha sub 2, and this right here is alpha sub 3. And that is kind of my estimated effect for each of these factor levels on growth. So like there exists a true alpha 1, alpha 2, alpha 3, and I'm kind of estimating them with this model. So it's kind of like an alpha hat 1, alpha hat 2, alpha hat 3, I guess, if we want to be consistent with our notation. So yeah. Now, assumptions when we're working with the categorical model like this, like one-way ANOVA, is that we do like the kind of the strict assumption is that the response variable at each level is approximately normally distributed about some group mean. Now, we don't actually need this to be true. Like we can actually make a more relaxed assumption using the central limit theorem here and just say that the distribution of possible sample means from each level is normally distributed. So if we think about repeatedly sampling, in this case, I think it's 30 observations that I simulated per group. If I think about continuously sampling 30 observations per group, plotting the sample mean that I got, and doing that over and over and over again, I just want that the distribution of sample means to be normally distributed, even if the underlying distribution here might not quite be normally distributed. That's really the thing that I need to be true. So the more relaxed assumption that's totally okay is that we just need that the distribution of possible sample means for each level is normally distributed, which we can say because of the central limit theorem if our sample size is sufficiently large. Now, nobody can tell you a number and say that above this number it will always be true. However, you'll commonly see benchmark numbers like in ANOVA, you commonly see like 20, 25, or 30. It's kind of like if you have at least that many observations per group, then you probably have this assumption. The central limit theorem is probably going to apply by this point. So we'll kind of, you might see that in an exercise on the homework, but just kind of keep that in mind that the strict assumption is that the group distributions are already normal. The relaxed assumption is that I have enough observations such that the central limit theorem will apply and my sampling distributions of each will be normally distributed. Secondly, the observations within each group should be random independent observations. So I think I mentioned the vitamin D COVID-19 study in a previous video. That would not fit this assumption here. So it's not just that I have 500 people doing one intervention, 300 people doing the other. They're selected by ward. So then really what I have is kind of clusters. I have 5 clusters in one group and 3 clusters in the other, and that's a little bit different. So you want all the observations within a group to be independent of one another and kind of representative of the populations, of the group populations that they're coming from. Okay, so that kind of goes into the error terms being normally distributed and independent. All right, so the variance of the response variable, oh, sorry, this one, okay, that makes a lot more sense. This goes with this term right here. I was like, wait a second, I don't think that's right. The variance of the response variable for each group should be normally distributed, such that I have kind of these normally distributed error terms. The other thing that's kind of important here, going along with this assumption, is that we're assuming that the variance of each of the groups is also the same. In other words, if I'm looking at these different groups, that I have about the same amount of variability coming from each of these groups. Now, they're not going to be exactly the same. They're going to have some variation. That's totally okay, and that's where kind of this more relaxed assumption comes in. ANOVA is actually a robust enough method that the variances can be pretty different, but typically the assumption that you're going to see is that no sample variance should be more than 5 times larger than another. If that's the case, then you might have to look into a different method besides a one-way ANOVA for comparing these groups if you have wildly different variances among your groups. But in general, we're assuming normally distributed errors within each group, and we're assuming a relatively constant variance. Okay, so just a quick word about two-sample t-test versus one-way ANOVA, and I will go over here. So a two-sample t-test is, essentially this model that we looked at, which is two-factor level. So y sub ij equals mu plus some alpha factor, some effect associated with which group it comes from, plus the error for each term. And if I only have two groups, this is a pretty easy comparison in terms of just directly comparing two means, coming up with some representation of the variability that I should expect by random chance, and doing a t-test. So then I would just observe how many standard errors apart my two sample means are, and whether that is within a normal realm of distance by random chance, or if it's too far away such that I don't expect this to be random chance difference anymore. The tricky part of a one-way ANOVA context is that I can't just compare two means. I have a bunch of pairwise comparisons that I could consider here. So if I have 3 or more means, then a two-sample t-test is not going to work unless I'm just doing a bunch of separate two-sample t-tests. But then that gets me into some problems, because if I'm calculating, say, a p-value multiple times, which I think we'll talk about this in a later video as well. If I do, let's say, 20 different two-sample t-tests, then by random chance, I would expect maybe one of them to have a p-value below, say, 5% by random chance, because that's what happens. That's probabilistically what's going on when I calculate a p-value under the null hypothesis and observe what happens. So that's why doing a bunch of pairwise tests is not necessarily the way to go. There are, as we'll talk about when we get to ad hoc or post-ad hoc testing, how we kind of think about this challenge. But it kind of sets up the reason for why we do one-way ANOVA in the first place, is that instead of just doing a bunch of separate independent pairwise comparisons, let's do one analysis that pulls all my information together at the same time and looks at whether or not my means could plausibly be coming from the same population mean or not. So I basically combine my within group variance. I find kind of an average within group variance and compare it to kind of this average between group variance to see if this seems to fit, if this seems to make sense under the null hypothesis that they're all coming from distributions with the same means, or if the differences are just too unusual to make sense under that null hypothesis. So kind of the decomposition of variance, we've actually seen this sort of before with the regression f-test, because we're kind of doing the same, we're doing an f-test again, just under a different context, is that we have a total amount of variation here, right? So we have SST is representing the total variation from each of my individual observations from the global mean. So I have kind of my estimate for the global mean right here. So this is estimate from you. I think earlier I said something about like, we could call this X bar, and I guess I should have said Y bar since we're talking about the response variable, but it's, all contextual. Like, I guess I could call it X and X bar for the response, but I guess Y bar is consistent with how we think about it here. This is my estimate from you, the global mean. And these are my individual observations. And I'm seeing how much variation I have from each of my individual observations from this global mean that I have for my sample. So I'm going to find the square deviations, I'm going to add them all up, and I'm going to call that my sum of squares total. So this right here is called sum of squares total. And this is the sum of all my squared deviations. You can think of them like as your squared residuals, if you want to use our regression term earlier. And I am decomposing that variance into two pieces. One is the variance that I'm observing within each individual group. That's this SS within, so sum of squares within. And I'm also decomposing that into the sum of squares between groups. And while we're not going to mathematically show why this is true, I think you can kind of look at it and figure it out if you wanted to. This is something I remember doing in grad school, actually, as an exercise. The sum of squares total is going to be the sum of your sum of squares between and your sum of squares within. These two terms make up your entire total variance. However, this representation here, so this sum of squares between is measuring how much variation we have within each group with respect to its group mean. So it's looking kind of like how much variation, if I use the group mean as an estimate, how much variation do I see? And I'm comparing that to how much variation there is from one group mean to each other in relation to the global mean here. So the idea is if this factor level, or if this factor variable is really helpful in modeling the response, then the sum of squares within is going to be a lot smaller in relation to the sum of squares total, and the sum of squares between is going to be a lot larger in relation to the sum of squares total, right? Because that means that there's not a whole lot of variation left if I'm using the group means as my estimates, and there's a lot of variation from group to group if the factor variable actually matters in predicting the response variable. So I have this visual aid just again to kind of point out these things. If you want to think about the sum of squares total is like this. Now it's doing like individual calculations, right? So it's kind of finding like this value to this value, this value to this value, this value to this value, and like squaring all those differences, right, and adding them up. But if you want to just think of it this way, sum of squares total is this entire range of values. It is all this variation that I have in this response variable when I don't use a factor variable. Now, when I do a one-way ANOVA and I decompose this variation, I now have two pieces. I have the average variance within, which is going to be kind of like the average amount that I'm seeing. Well, it's not really an average yet, it's just the total. So it's like all this variation, which is spanning this much, range, in comparison to kind of these group means and the variation from group mean to group mean, which is going to be like something more like this. And I'm looking at, how shall I do this? I'm going to do kind of like this. Use that dashed lines to kind of show you like how I have some variation here among my groups, and that's kind of represented by my sum of squares between. So if I look at this variation from group mean to group mean plus the variation within each of the individual groups, that should equal the total amount of variation that I began with in this first line. And as you can kind of imagine, I can construct different visuals that tell different stories here, right? So if I have a situation that looks like, this, where I have my group means are just like, wildly apart from one another, So here, like my within, oh, I need to go out of here. So my within variance over here is going to be quite low, and my between variance is going to be quite high in this context. This would be an example where our factor variable is making a big difference in cutting out some of that variation, and I have a lot less unexplained variation if I account for the group. I can also construct a scenario where, oh, that's way too big. I can also construct a scenario where the noise is just so big in relation to the actual difference that I'm observing between the groups, such that it doesn't really matter, and I might have a much harder time rejecting the null hypothesis and saying that, yeah, these are beyond random chance differences, when it's like, well, honestly, all of these could have come from the same distribution with the same mean, right? So if I look at this, that seems more plausible than that previous drawing that I drew, where it's like, yeah, this seems like way too odd to happen by random chance if this factor variable doesn't actually matter in predicting the response. So yeah, that's what's going on visually. We have sum of squares total being broken down into two pieces. So we have our variation to begin with that we can now represent into two different measures of variation, the variation within each group, in addition to the variation from group to group. We're not really going to worry much about calculating any of this by hand because R will do it for us. We just want to understand kind of the logic going in here. That when you do an ANOVA in R, you'll get something called an ANOVA table if you do a summary of your ANOVA model. I'll just kind of mention this table in the book that I'm attaching here switches around degrees of freedom and sum of squares from how R will output it to you. But these are the same values. R also leaves off the total row down here. It just starts with within and between. But yeah, what's going on here is I am breaking down my variation, but then I'm also dividing by this degrees of freedom value, which we kind of need to talk about a little bit. So the between sum of squares value is the variation from group to group, and I am dividing that by approximately the number of groups that I'm comparing. So kind of ignore the -1 and the -g for a second and just think about this as dividing by number of groups. So what's going on here is to make the average sum of squares between, I take this value and divide by approximately the number of groups, technically it's number of groups -1, to kind of approximate the average variation between one particular group mean and the global mean. So it's kind of that average between variation going on there. Now, the reason we divide by g-1 instead of just g is because of the error correction. It has to do with the fact that we're estimating the global mean with y bar. This is not going to be accurate. We're going to slightly underestimate the true variance with this measure because our sample means are conveniently located right around our sample mean and not the global mean. So because of bias, we divide by g-1 instead of g to make this what's called an unbiased statistic. But the conceptual idea here is I'm dividing by approximately the number of groups that I'm comparing to get kind of an average group mean departure from the global mean. With sum of squares within, I'm dividing approximately by the number of observations that I have to find kind of an average amount of variation per observation that I'm looking at. Now we do again do an error correction, so it's not going to be just n, it's going to be n minus g, and that has to do with the fact that we're estimating all of these group means. So for every group mean that I estimate, I have a degree of freedom that I lose, and to make this an unbiased statistic, I have to correct for that in my denominator by dividing by a slightly smaller number. Smaller number? Yeah, dividing by a smaller number to make this a larger variance. Yes, okay. So yeah, again, degrees of freedom is tricky. The idea of bias is confusing. As long as you kind of know conceptually we're dividing by n and dividing by g, that's sort of what's going on here. And so that gives us what we call these mean square errors, or kind of these average variance between average variance within, which we can now put together in an F ratio and into an S statistic. And so we can see how much variation we have between our groups and how much variation we have within our groups. if this value is somewhere in the neighborhood of 1, it means that our grouping factor doesn't really matter that much, that it seems to just be doing random chance explanation. If our F ratio is getting higher and higher, it means that we're seeing more variation explained by the between group variance than we would expect by random chance. So typically, when our F ratio gets to 3 or 4 or 5, that's when we're starting to say, yeah, the between variance is a lot higher than we would expect by random chance if this factor variable didn't actually do anything, and this was just random chance differences I observed between groups. So yeah, I'm trying to think. Oh yeah, and that's all we do in this video, but we'll talk about more about one-way ANOVA and such in the following videos as well.